Hello students, in today's video we are going to discuss about the multiplexers. A digital multiplexer is a combinational circuit device that converts many of input information signals into one output. That means our multiplexer, it is a combinational circuit. What is a combinational circuit? Combinational circuits are those circuits that does not possess the memory. Actually, in my previous videos I have already discussed with you that in digital electronics we can have two types of the circuits. One of them is in sequential circuit and another one is in combinational circuit. Sequential circuits are those that possess the memory, and combinational circuits that does not possess the memory, and multiplexer is one of the type of that circuit. It accepts many inputs but gives only one output. So if we have n number of the inputs to the multiplexer, it will select from these n inputs only one input as its output. So therefore it is also known as the data selector. Now multiplexers are used to perform high speed switching. Multiplexers handle two types of the data, that is analog and digital. For analog applications, multiplexers are built of relays and transistor switches. For digital applications, they are built from standard logic gates. So basically in this video, we are going to focus on the standard logic gates, or I can say that how we can implement a multiplexer using the standard logic circuits or standard logic gates. That means we are totally focusing on the digital multiplexers. Now a multiplexer used for digital applications, that is also known as the digital multiplexer. That is a circuit with many inputs but only one output. As I told you that in multiplexers we can have n number of the inputs but only one output. So any one of the input from these will be taken as the output of the multiplexer. That depends upon the selection lines. Those selection lines are known as the control signals. So therefore in multiplexers we apply these control signals. They can steer any input to the output. That means if we are having n number of the inputs, based on the selection lines of the multiplexers, any one among these n lines are selected as the output of the multiplexers. So we can have number of types of the multiplexers, or we can say the digital multiplexers in the digital electronics. We can have 2 cross 1 mux. Multiplexer is also known as the mux, or we can say 2 to 1 mux. Then we can have 4 to 1, 8 to 1, 16 to 1 multiplexers. 2 cross 1 mux, it takes two number of inputs and selects just one as an output. Similarly, we can have 4 cross 1. That means we can have in this 4 number of the inputs and then only one output. Multiplexers always give only one output. This is the property of the multiplexer, that it just selects any one of its input as its output, but only one. We can have 4 cross 1 multiplexer, 8 cross 1 multiplexer, 16 cross 1 multiplexers, but the property is that it just selects only one input as its output. So it is therefore known as the data selector. So it just selects one of the input line as its output. So we can have 4 cross 1 multiplexer, or we can say 4 cross 1 mux, or we can say 8 to 1 mux, or 16 to 1 multiplexer. So in this today's video we will just focus on the 4 cross 1 multiplexer. Therefore in the 4 cross 1 multiplexer we will be having 4 input and only one output, but that output from among these 4 inputs is selected by the selection lines. So see, here is a block diagram, in which we have 4 number of the inputs. This is actually the block diagram of the 4x1 multiplexer. You can see from the diagram that we are having here 4 input lines, line 1, line 2, line 3 and line 4. So we are having the 4 number of the inputs and then only one output. I have told you that multiplexers will always give only one output, and this output will be based upon any one of the input line of the multiplexer, but that will be decided by the selectors. These are the selectors or the selection lines of the multiplexers. And one more thing is there on a multiplexer circuit, that is the enable line. This enable line is basically required to switch on or off this multiplexers. So suppose in certain circuitry sometimes we don't want that multiplexers should function for a certain point of time. For the certain moment we just need that our multiplexer should not work. At that time in this enable line we give its input as 0 so that it will be disabled, and then when we require the multiplexer again in that particular digital circuitry, at that time we put this enable as 1. So you will see in our next slide that multiplexers are basically implemented by using the AND gates. So whenever we give the input, so this input enable is given to every gate, every AND gate of the multiplexer. So whenever there is a 0 on the AND gate, it obviously gives us 0 as an output, because AND requires all its inputs as 1 so that it will be high. So when we give the enable as 0, so the multiplexer at that time will be disabled. So that's why we have kept this enable line as one of the input to the multiplexer. So basically one more important thing here is that if we have 2 raised to the power n input lines, then n represents the number of the selection lines. So therefore that means, see from this block diagram, as I have told you that this is 4x1 mux, that means we have here 4 number of the input lines and only one output line. So therefore it means that we are having 2 raised to the power 2. 2 raised to the power 2 is equal to 4. That means here n is equal to 2. So therefore n represents the number of the selection lines. So in this case we are having 4 inputs. That means 2 raised to the power 2 input lines. That means n is 2. Therefore if we are having 4 input lines, n in that case will be equal to 2. Therefore we have to take 2 selection lines in implementing the 4x1 multiplexer. So here we have the n is equal to 2. So similarly for 8x1 multiplexer you can have 2 raised to the power 3. 2 raised to the power 3 is 8. So in that case our selection lines will be 3. So as I have told you, the output of the multiplexer is decided by the input on the selection lines. So we will just see its implementation, how we can implement the circuit and how we can just make its Boolean expression so that we can just make the circuit and the truth table and the other things involved in the 4x1 multiplexer. So as I have told you that this video will generally focus on the 4 to 1 multiplexer, and then similarly you can do 8x1 multiplexer or 16x1 multiplexer. You can do that similarly the way we will do the 4 to 1 multiplexer. So 4x1 multiplexer, as I have shown you already the block diagram of 4x1 multiplexer. So it is a digital device which converts 4 input signals into 1 output signal, and it is controlled by 2 selection lines. And I have already discussed with you that selection lines are decided by the formula 2 raised to the power n, where n represents the selection line and 2 raised to the power n represents the total number of the input lines to the multiplexer. See, you can see here, I have just shown here the diagram. We have the block diagram of the 4x1 multiplexer. It is clear from this, and then the truth table, and then the circuitry. So before moving to the circuit, we will just first of all discuss about the truth table of the 4x1 multiplexer, and after the truth table of the 4x1 multiplexer, we have to first make the Boolean expression, and based on that Boolean expression we make the logical circuit of the multiplexer. So as I have told you, we just discussed about the 4x1 multiplexer, the block diagram of 4x1 multiplexer. It will be having 4 number of the inputs and 2 number of the selection lines and 1 output. Multiplexers always give one as only one output. So basically we can have D0 as its output, we can have D1 as its output, we can have D2 as its output, or we can have D3 as its output, but all this is decided by the selection lines. So the number of the selection lines in this case is 2 raised to the power 2. That means n here is equal to 2. The number of the selection lines here are 2. So we have taken selection lines as S1 and S0. How many combinations will 2 give? It will give 4 combinations. So that is what we need in order to make this multiplexer. So we have S1, S0 as the selection line. So based on these selection lines we decide about the output of the multiplexer. So if S1 is equal to 0 and S0 is equal to 0, D0 is the output of the multiplexer. So at this input on the selection line, D0 will be enabled as an output. So as S1 is equal to 0 and S0 is equal to 1, D1 will be selected as its output. So at S1 is equal to 1 and S0 is equal to 0, D2 will be selected as its output. So at S1 is equal to 1 and S0 is equal to 1, D3 will be selected as it is output. So that means based on the input on the selection lines, the output is decided, whether the output will be D0, D1, D2 or D3. This is decided by the input on the selection lines. So now we are done with the truth table of the multiplexer. So out of this truth table we can make the Boolean expression. We can give the Boolean expression of the multiplexer. So based on this we have to make a Boolean expression. That means the Boolean expression here simply will go like, we don't have to solve it using the K-map, or we don't have to just simplify the Boolean expression using any Boolean law or the Boolean or the K-maps. We will just simply write an expression here of this truth table. So if you will see, we have S1 complement, S0 complement and D0, then or S1 complement S1 and D1, then S1 and S0 complement and D2, or S1 S0 D3. So this is what the Boolean expression will look like. That means output will be selected, because we are placing here or, because out of these 4 any one of them will be selected as the output of the multiplexer. So its Boolean expression will be like S1 complement S0 complement D0, or S1 S0 complement D1, or S1 complement S0 D2, or S1 S0 D3. That means any one of them will be selected. That means if I am taking S0 as S1 as 0 and S0 as 0, at that time D0 will be its output. Fine. And if I am taking S1 as 0 and S0 as 1, D1 will be its output. So that means any one of them, that means we are placing an OR operation between these expressions. So out of this Boolean expression, we are just making the logical circuit diagram of the 4x1 multiplexer, which is shown here. So what we are taking? We are taking D0, D1, D2, D3 as an input lines to these AND gates, and then we are just giving S1 and S0 as the selection lines, and at somewhere we are taking the NOT of S1 and NOT of S0, so therefore we are showing it using the NOT gate here. So wherever we require the NOT of S1, we take that as an input to the AND gate, and ultimately what we are doing, we are just keeping the OR gate here so that any one among them will be selected. So this logical circuit is basically built from this Boolean expression. So therefore it means that if S0 is equal to 0 and if S1 is equal to 0, then Y, that means the output, is equal to D0. That means at that time D0 will be selected as its output. So only first input is stayed across the output. If S0 is equal to 1, S1 is equal to 0, then Y is equal to D1. So the second input is stayed across the output, and so on for the rest of the two. So this is how we implement the 4 cross 1 multiplexer. Similarly, you can do, or you can implement the 8 cross 1 multiplexer or the 16 cross 1 multiplexers. The thing is like the procedure will be same, and there will be always just one thing you have to take care about is the number of the selection line. That means if you are taking if you are taking 8 cross 1 multiplexers, in that case what you have to do, you have to decide about the selection lines. At that time 2 raised to the power 3 is equal to 8. That means at that time you have to take 8 combinations. From out of those 8 combinations, you have to decide about which input will be treated as an output. So that means it requires 2 raised to power 3. That means it requires 3 selection lines, so that we take 3 as its selection line, and therefore we decide. Similarly, we make its truth table and then the Boolean expression, and similarly its logical circuit. So that's all for the today's video. Thank you for watching.